For thousands of years, astronomers across the globe have studied the movement of celestial objects. It's largely owing to their discoveries that we began to understand our universe. In India as well, astronomy has been a field of study for centuries now. India first ventured into space in the early 60s, when Dr. Vikram Sarabhai laid the blueprint of the Indian space program. It focused on the use of space technology for the benefit of the common man. With the deployment of PSLV, it was now possible for India to launch a payload of reasonable size into space. That was a precursor to India's long and exciting journey into the heart of the unknown. Since then, ISRO has systematically expanded its capabilities by launching projects with specific visions and goals. In 2008, ISRO launched its first planetary exploration with Chandrayaan-1, which lasted 312 days. The mission conducted studies to comprehend the nature of the lunar crust and the evolutionary history of our beloved satellite. It was in 2013 that ISRO turned its attention on Mars. Mangalyaan, India's Mars orbiter mission, completed 4 years in its orbit around the red planet. In fact, the story of the mission became so popular that it inspired a Bollywood film. Within 2 years, ISRO was ready with its next mission, AstroSat. As India's first dedicated multi-wavelength space observatory, it is fully enabled by a single satellite. ISRO's next significant stride into space was Chandrayaan-2, a complex mission to explore various facets of the moon. The Sun is another fascinating point of interest as it rules the movement of the Earth and other planets. With this in mind, India's upcoming Aditya L1 mission will study the Sun's upper atmosphere. India's space odyssey continues, emboldened by the many firsts for ISRO in the last decade. With Chandrayaan, Gaganyaan and other future missions, the aim is to deepen our understanding of the universe and our place in it. In line with the global agenda, ISRO will lead India into the next decade through expanded research and technology development to build future capabilities in space exploration. In the words of Dr. Vikram Sarabhai, we are convinced that if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. Today, as we continue to launch 1 billion dreams, the sky is no longer the limit for India. The sky has been an object of curiosity and wonder since time immemorial. For thousands of years, astronomers across the globe have studied the movement of celestial objects. It's largely owing to their discoveries that we began to understand our universe. In India as well, astronomy has been a field of study for centuries now. India first ventured into space in the early 60s, when Dr. Vikram Sarabhai laid the blueprint of the Indian space program. It focused on the use of space technology for the benefit of the common man. With the deployment of PSLV, it was now possible for India to launch a payload of reasonable size into space. That was a precursor to India's long and exciting journey into the heart of the unknown. Since then, ISRO has systematically expanded its capabilities by launching projects with specific visions and goals. In 2008, ISRO launched its first planetary exploration with Chandrayaan-1, which lasted 312 days. The mission conducted studies to comprehend the nature of the lunar crust and the evolutionary history of our beloved satellite. It was in 2013 that ISRO turned its attention on Mars. Mangalyaan, India's Mars orbiter mission, completed 4 years in its orbit around the red planet. In fact, the story of the mission became so popular that it inspired a Bollywood film. Within 2 years, ISRO was ready with its next mission, AstroSat. As India's first dedicated multi-wavelength space observatory, it is fully enabled by a single satellite. ISRO's next significant stride into space was Chandrayaan-2, a complex mission to explore various facets of the Moon. The Sun is another fascinating point of interest as it rules the movement of the Earth and other planets. With this in mind, India's upcoming Aditya L1 mission will study the Sun's upper atmosphere. India's space odyssey continues, emboldened by the many firsts for ISRO in the last decade. With Chandrayaan, Gaganyaan and other future missions, the aim is to deepen our understanding of the universe and our place in it. In line with the global agenda, ISRO will lead India into the next decade through expanded research and technology development to build future capabilities in space exploration. In the words of Dr. Vikram Sarabhai, we are convinced that if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. Today, as we continue to launch 1 billion dreams, the sky is no longer the limit for India. The sky has been an object of curiosity and wonder since time immemorial. For thousands of years, astronomers across the globe have studied the movement of celestial objects. It's largely owing to their discoveries that we began to understand our universe. In India as well, astronomy has been a field of study for centuries now. India first ventured into space in the early 60s, when Dr. Vikram Sarabhai laid the blueprint of the Indian space program. It focused on the use of space technology for the benefit of the common man. With the deployment of PSLV, it was now possible for India to launch a payload of reasonable size into space. That was a precursor to India's long and exciting journey into the heart of the unknown. Since then, ISRO has systematically expanded its capabilities by launching projects with specific visions and goals. In 2008, ISRO launched its first planetary exploration with Chandrayaan-1, which lasted 312 days. The mission conducted studies to comprehend the nature of the lunar crust and the evolutionary history of our beloved satellite. It was in 2013 that ISRO turned its attention on Mars. Mangalyaan, India's Mars orbiter mission, completed 4 years in its orbit around the red planet. In fact, the story of the mission became so popular that it inspired a Bollywood film. Within 2 years, ISRO was ready with its next mission, AstroSat. As India's first dedicated multi-wavelength space observatory, it is fully enabled by a single satellite. ISRO's next significant stride into space was Chandrayaan-2, a complex mission to explore various facets of the Moon. The Sun is another fascinating point of interest as it rules the movement of the Earth and other planets. With this in mind, India's upcoming Aditya L1 mission will study the Sun's upper atmosphere. India's space odyssey continues, emboldened by the many firsts for ISRO in the last decade. With Chandrayaan, Gaganyaan and other future missions, the aim is to deepen our understanding of the universe and our place in it. In line with the global agenda, ISRO will lead India into the next decade through expanded research and technology development to build future capabilities in space exploration. In the words of Dr. Vikram Sarabhai, we are convinced that if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. Today, as we continue to launch 1 billion dreams, the sky is no longer the limit for India. The sky has been an object of curiosity and wonder since time immemorial. For thousands of years, astronomers across the globe have studied the movement of celestial objects. It's largely owing to their discoveries that we began to understand our universe. In India as well, astronomy has been a field of study for centuries now. India first ventured into space in the early 60s, when Dr. Vikram Sarabhai laid the blueprint of the Indian space program. It focused on the use of space technology for the benefit of the common man. With the deployment of PSLV, it was now possible for India to launch a payload of reasonable size into space. That was a precursor to India's long and exciting journey into the heart of the unknown. Since then, ISRO has systematically expanded its capabilities by launching projects with specific visions and goals. In 2008, ISRO launched its first planetary exploration with Chandrayaan-1, which lasted 312 days. The mission conducted studies to comprehend the nature of the lunar crust and the evolutionary history of our beloved satellite. It was in 2013 that ISRO turned its attention on Mars. Mangalyaan, India's Mars orbiter mission, completed 4 years in its orbit around the red planet. In fact, the story of the mission became so popular that it inspired a Bollywood film. Within 2 years, ISRO was ready with its next mission, AstroSat. As India's first dedicated multi-wavelength space observatory, it is fully enabled by a single satellite. ISRO's next significant stride into space was Chandrayaan-2, a complex mission to explore various facets of the moon. The Sun is another fascinating point of interest as it rules the movement of the Earth and other planets. With this in mind, India's upcoming Aditya L1 mission will study the Sun's upper atmosphere. India's space odyssey continues, emboldened by the many firsts for ISRO in the last decade. With Chandrayaan, Gaganyaan and other future missions, the aim is to deepen our understanding of the universe and our place in it. In line with the global agenda, ISRO will lead India into the next decade through expanded research and technology development to build future capabilities in space exploration. In the words of Dr. Vikram Sarabhai, we are convinced that if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. Today, as we continue to launch a billion dreams, the sky is no longer the limit for India. The sky has been an object of curiosity and wonder since time immemorial. For thousands of years, astronomers across the globe have studied the movement of celestial objects. It's largely owing to their discoveries that we began to understand our universe. In India as well, astronomy has been a field of study for centuries now. India first ventured into space in the early 60s, when Dr. Vikram Sarabhai laid the blueprint of the Indian space program. It focused on the use of space technology for the benefit of the common man. With the deployment of PSLV, it was now possible for India to launch a payload of reasonable size into space. That was a precursor to India's long and exciting journey into the heart of the unknown. Since then, ISRO has systematically expanded its capabilities by launching projects with specific visions and goals. In 2008, ISRO launched its first planetary exploration with Chandrayaan-1, which lasted 312 days. The mission conducted studies to comprehend the nature of the lunar crust and the evolutionary history of our beloved satellite. It was in 2013 that ISRO turned its attention on Mars. Mangalyaan, India's Mars orbiter mission, completed 4 years in its orbit.
Yes, sir.
Okay, sir. Shall I start?
Yeah. So I request I request Dr. Nirvikar to chair this session.
Thank you, sir. Thank you, Tarun sir, and thank you, our session chair, Kishore ji. In this session, we have total 8 presentations, and I hope all 8 presenters are available. I can see the first presentation.
Except number 12, I suppose.
Number 12, okay. Yeah, RP Singh, maybe we'll see at the time when is scheduled. So the first presentation is by Ms. Ritambara Datta on impact of stratospheric ozone and mesospheric tides on enhanced occurrence of 150 km echoes in year 2019. Ritambara, you can begin your presentation.
Your voice is breaking up, Nirvikar.
Oh.
Okay. Okay, sir.
Yeah, Ritambara, you can begin your presentation, and you have 12 minutes. And please leave 3 minutes for some questions and discussion. Please go ahead.
Sure, sir. Okay. Good evening, everyone. I am Ritambara Datta, and I am working as a senior research fellow in National Atmospheric Research Laboratory. And today I will talk about the impact of stratospheric ozone and mesospheric tides on the enhanced occurrence of 150 km echoes in the year 2019. So the outline of my talk today is, in the introduction, I will first talk about the 150 km echoes and its characteristics. Then I will talk about the different types of echoes and how they are differentiated with each other. And then next I will come to the data methodology part, where I will say about the instruments I have used in my study. And then in the results section, I will start with the seasonal and interannual variation of these echoes and how they are related to the solar activity periods. And then I will talk about the echoes during 2019 and how they are different from other years. That is, in my study, I have used from 2016 to 19. So how they are different from 2016 to 18. So then I will show some ionosonde observations, and finally I will talk about some possible source origin in the middle atmosphere for these echoes. So 150 km echoes, these are first reported by Balsley in the year 1964 from the Icamarca Radio Observatory. The figure shows the first observation of the 150 km echoes, where near to this 150 km range, we see as amplitude increase of the radar signal. So when seen in an RTI plot, that is range time intensity plot, it shows a clear necklace shape pattern, that is having a forenoon descent shape and an afternoon ascent structure. And it occurs mainly in the height region of 130 to 170 kilometers, which is also known as the equatorial low latitude valley regions. And it occurs mainly in daytime, only in daytime, and it is the time is 9 to 15 hours local time. And it is seen in the equatorial and low latitudinal regions. But its interesting feature, it has very high day-to-day variability in its structures and characteristics. And its quasi-periodic nature, that is in the order of 5 to 15 minutes, has been seen in these echoes, which indicates the possible role of gravity waves in its generation. So basically, there are two types of echoes. One is this type A echo, another is this type B echo, which I will discuss in the next slides. So these are some of the previous works done in this field using either using these high sensitive radars like from Icamarca or from MST radar from Kadanki, and also from some low sensitive radars like EAR Kototabang. Although the characteristics of these echoes has been studied widely for these equatorial locations, but still the exact source origin for these echoes is still a confusing topic. So I will come to this different types of echoes. And the first is the type A echoes. These are seen to have very weak SNR values and a very prominent nucleus shape, that is descending pattern roughly before this noon time, and also some ascending patterns in the afternoon time. It is said to be only predominant, that is, it has been seen that compared to type B echoes, type A echoes occurs more in number. But they can occur independently, that is, without the presence of type B echoes also, this can be found. And this can be best observed when it is the perpendicular to the magnetic field. Here SNR is also seen to depend on the spectral width. And since it has a very weak SNR, so it can be detected by only high sensitive radars like from Ikamarka or Gadanki. Come to this type B echoes. These are having comparatively stronger SNR values, and they occur in much less number than this type A echoes. And interestingly, it is seen that it cannot occur alone. That is, it is always embedded and superimposed in this type A echoes, but they can be only observed perpendicular to the Earth's magnetic field. And here SNR seem to be independent of the spectral width, and because of its strong SNR value, it can only be detected by low sensitive radars. It can even be detected by these low sensitive radars, like from EAR Kotota Bang. So this is the data methodology part. So I have taken my radar observations from this equatorial atmospheric radar EAR over Kotota Bang, which is present at 0.0 degrees south and 10.36 degrees south deep latitude in Indonesia. It operates at a frequency of 47 megahertz and with a peak power of 100 kilowatts and average power of like 5 kilowatts. And since it has lower sensitivity, so it can only detect this type B echoes. Then I will show some sample anagram observations which I have taken from this ionosonde present over Kotota Bang, Indonesia. It is working at a frequency of 30 megahertz with a peak power of 20 watts. And some ozone and temperature data I have taken from the SABRE instrument on board this TIME satellite. The temperature data is used for the tidal analysis calculations. So coming to my results and discussion part. So this is the seasonal and interannual variabilities of the 150 kilometer echoes, what I observed over Kotota Bang. And I want to mention that these are all type B echoes. First, I want to mention that there is no data over here in October 2019, so there is a data gap. Then by seeing these features, we can see that there is a maximum occurrence of these echoes during this boreal summer and boreal winter months. That is, the period covering is June to August and December to January of 2016 to 19, which is also the descending phase of the solar cycle 24. As we see that this echo maxima as well as the occurrence of these echoes, this spreads as we move from the solar moderate to solar minimum years. That is, as we go from this 2016 to 19, it is increasing. Minimum echo is observed during this March to April time and also during September to October time. This is the equinox times. But an interesting feature is I have observed that there is a high anomalous increase of these echoes during the year 2019, which is represented by this black line, particularly during September 2019, which is showing a PO of 76%. So in order to identify the real reason behind this, so we have segregated this type B echoes into weaker SNR echoes and stronger SNR echoes. And we have seen that weaker echoes are mostly present in most of the days of 2018, while these higher SNR echoes are present in 2019. And the higher SNR echoes are associated with descending structures, as we can see. And it is seen that this rate of these descending structures is approximately 6.5 kilometer per hour, which is also similar to the rate of downward phase progression of the semidiurnal tidal winds, which is approximately 7 kilometer per hour. So which implies a possible role of semidiurnal tidal winds in its generation. And also it is to be mentioned here that it is present in all geomagnetically quiet days of September 2019, and also much more amount during this June to August 2019, and also this December 2018 to January 2019, which is including our boreal SSW period. So the more population of this high SNR echoes in 2019 thus can be related to the semidiurnal tidal activity because of its descending structures. So next I will show some sample ionogram observations. I want to say here that in Patra 2011, he has showed that the intermediate ion layers, which are associated with these descending echoing structures, they are formed by the semidiurnal tidal winds, indicating so the tidal presence in this formation. And also from our observations, we have seen that there is a descending ion layer, which we can see this from this ionogram pictures. And they are occurring during this geomagnetically quiet days and also during this echoing hours. So 3 days I have shown here. One is this 8th, 11th and 12th of September, where during this echo hours, it is seen to be descending from this 160 kilometers, 150 kilometer and 156 kilometer respectively. Again, indicating the presence of this tidal winds via this. So next I will come to some tidal analysis which I have done, and I will show some latitudinal variation of this DW1 tide, SW2 tide and D3 tide. So in DW1 tide, a semi-annual variation is seen, and it's seen that the maximum amplitude is over the equator during March to April and also during September to October prominently. But an interesting feature comes out here that in 2017 and 2019, the amplitude is becoming less after this March-April time. So compared to the years like 2016 and 18. For SW tide also, we have seen that the maximum amplitude is over this 30 south to 40 south during this February to May time, and also during this 40 north during this October to February time. And for D3 tide, this maximum amplitude is seen over the tropical regions during this June to September months. So in order to infer the relation between this DW1 tide and the percentage of occurrence of this echoes, we have done a correlation analysis, and we have seen that DW1 is significantly related to this percentage of occurrence of these echoes, both during 2018 and 19. So this clearly indicates that the relative separation of DW1 tide during these years are becoming important for this observation of this high occurrence of POs. It is suggested that maybe the separation of DW1 may lead to the relative enhancement of this SW2 tide over DW1 tide. So for seeing this, we have also plotted this ozone VMR variation at different heights from 10 hectopascal to 1 hectopascal, and also at different equatorial latitudes. So one is this equator and also 10 north and 10 south. And the main reason is because this SW tide is also highly generated with this solar insolation absorption by ozone molecules in the stratosphere and mesosphere. It is seen from this graph that during this 2017 and 2019, there is high increase of this ozone VMR values, which is also corresponding to the Vaker DW1 activity periods, because these 2 years we have seen that this amplitude is decreasing for this DW1 tide. Another thing I have seen that there is an enhancement in the ozone during September 2019, which is due to an austral minor SSW which has occurred, which has increased the ozone molecules at the equatorial latitudes. So I want to mention here that as per this GSW1 tidal result, which is showing that DW1 is principally forced by the absorption of solar absorption by tropospheric water vapor, and it is out of phase with the solar insolation absorption by the stratospheric and mesospheric ozone. So the former actually suppress the latter. So it happens that this relative separation of this DW1 tide during 2017 and 19, that may have led to the relative dominance of this SW2 tide during these years, and thus implying the significant role of this SW2 tide in the high echo occurrence of this in 2019. So finally, I will summarize my results and come to some conclusion that what I have got here is the seasonal variation of these echoes is very clear during these low solar activity periods, and it is seen to be having higher percentage of occurrence during June to August time and also during December to January time. Particularly, the PO is extremely high in 2019, the whole year, throughout the year, which is a solar minima year, particularly in this September 2019, which also includes an austral SSW period. And the descending structures of these high SNR echoes are seen to be more populous in the year 2019 compared to other years. And the descent rate of these echoes are seen to be very much comparable with the downward progression of the semidiurnal tidal wind. So this indicates a role of semidiurnal tidal winds in its generation. And from this GSWM result also we have seen that this relative enhancement of SW2 over TW1 tide over these years, which are having higher ozone values, that can be one of the reason we can say as this higher PO occurrence of this ecos during 2019. So it is suggested that this meridional wind shear, which is associated with this SW2 tide, that may form an interchange instability developed on the gradient of this descending ion layer. And also one important condition is here with solar minimum condition in 2019. This altogether may are responsible for the required plasma irregularities, which may be responsible for this high SNR descending structured ecos. This work is published in this Advances in Space Research 2021. So this is all about today. Thank you.
Thank you, Ritambara. We
Yes,
have
sir.
some time for few questions. Anybody?
Yes, sir.
I do not see any hand raising or no voices there for questions.
Okay, sir.
I have one
Yes, sir.
question.
Chat box, there is one question from Ramesh.
Okay, yeah, I can read that. Thank you, sir.
Yeah,
Thank you for
may I know what is the implication of negative correlation between DW1 and PO? That is, the ecos are not due to DW1. What is the descent rate? What is the descent rate of these ecos? Whether they are same as DW1 or SW2?
The descent rate of these ecos are similar to the SW2, but we have seen that if ozone is increasing, this tides should also increase, that DW1 and SW2. But from this DW1 is showing a different characteristics because it is principally governed by this tropospheric water vapor. So it is, if it is less, so it is becoming, so that is why I have used the term the relative dominance of SW2. So here SW2 is taking a more part and it is contributing to this eco generation. So the the relative separation of this DW1 tide is becoming important.
Okay, I think Mesh might have noted the answer. I have one small query.
Yes. Yes, sir.
You are showing the descending layer in ionogram.
Yes, sir.
You are showing 150 kilometer one particular level. Can you go to that slide if you have that? Otherwise, also you can answer me whether you
Yes.
use the virtual or the true height.
That is the virtual height, sir.
So, do you think this virtual height will correspond to the true height of 150 kilometer eco, or how you are going to correspond this thing? I'm not getting any point. Why are you showing 150 kilometer at that level?
Actually, from ionosonde observations, we have seen from in that region, this descending ion layers is being observed for these days, and it is also descending like this height. Particularly, I have shown like 160, 150, but it is before this time also it is coming. So so their presence can be seen from this ionogram data. Here only I am showing that particular 1 or 2 times, like it is existing for 2 hours, 4 hours, like that. But one time I just selected and showed.
Correct. That's fine. But whether the virtual or true height analysis, which one you will prefer?
Actually, from this ionosonde, we are getting this virtual height. So later we can pursue with this in this. I will see. So.
Okay. So one more. Shripati is having. Yeah, please, Shripati. Quick question.
Yeah,
Yes,
I just wanted to see what is the ionogram that you are showing. I missed that slide.
Chitambra, can you show the
yes, sir,
slides?
I'm trying actually.
No problem. If you have not answered. Yeah, Shripati, please ask the question.
Yeah, actually, I want to know how you are identifying the 150 kilometer echo in ionogram.
No. She is not identifying. She has shown
No.
one particular. Yeah, you please.
Okay. This is
It is
the
only descending eyelids I'm showing.
Higher height she is showing. Higher
okay,
height.
okay. Very good. Okay, fine.
Correct. Yeah.
Okay, sir.
Yeah,
Okay.
yeah.
So I think with this we complete this presentation. Thank you, Ritumira. We
Thank
move
you,
on
sir.
to we move on to next presentation by Sovan Saha from Physical Research Laboratory, Ahmedabad. He will be presenting on OI 630 nanometer night glow variability during post-sunset time over low latitude thermosphere. Sovan, are you there?
Yes. So I hope I am audible. I have shared my screen also.
Yeah, please make it full screen. Yeah, everything is right to go. So you have 12 minutes, Sohan and Sohan, and yeah, we will have some discussion. Yeah, thank you. Please go.
Okay, thank you. So good afternoon, everyone. Myself, Shobhan Shah. I am a senior research fellow at Physical Research Laboratory. First of all, thanks to the organizer committee of NSSS for giving me opportunity to present my work here. So today I'll be going to discuss about the oxygen 630 nanometer night glow variability during post-sunset time over a low latitude thermosphere. So starting with the science motivation of my study, during daytime, due to the eastward electric field over the equatorial F region, the equosby dip, that is vertically upward, and plasma it uplifted over the high altitude region, and then it comes down to the low latitudinal region through the geomagnetic field lines. So in this way, the plasma distribution happens over the low latitude region. Now, due to this reason, the either side of the geomagnetic equator, there is a larger plasma density can be observed. So this is called the equatorial ionization anomaly, and this is a daytime phenomena. Now, in the right side, it shows the vertical drift over the equatorial region. The observation taken from Hikamarka, that is the American longitudinal sector. Now, during daytime, the vertical drift is in the upward direction, which was shown here also. And the night time, the vertical drift is in the downward direction. Now, in between, when the day to night transition happens, there is a larger vertical drift has been observed, which is called as a pre-reversal enhancement. Now, similar process, the resurgence of EIA, similar thing can generate or reinitiated during this PRE, and the plasma distribution will again initiated, and the plasma distribution will happen over the low latitude region. So our observation location, which is Mount Abu, which is located in the northern crest of the equatorial ionization anomaly, will be affected due to this several electrodynamic processes. Now, to study the upper atmospheric processes, we use oxygen 630 nanometer night glow emission, which originate around 250 kilometer altitude. And we observed this emission using the high throughput imaging initial spectrograph. The mechanism of this night glow oxygen 630 nanometer emission is associated with the dissociative recombination of the molecular oxygen. The schematic of the optical instrument, it looks like this is a slit spectrograph. The slit is oriented in the north-south direction, and the red line emission line, it looks like this. And the y-axis, it shows the spatial distance from north to south. It provides a spatial information. Now, coming to the observation, the oxygen 630 nanometer emission during the night time. So after the sunset, there is a ionization stops, only recombination is present. Therefore, monotonic decrement happens in the oxygen 630 nanometer night glow emission. And this vertical line, it shows the uncertainty in measurement. Now, from a nearby location, Ahmedabad, which is situated around 1.6 degree away from the observation location Mount Abu. Now, over Ahmedabad, there is a DigiSound instrument is operating. From there, we have used the measured electron density, and we have estimated the oxygen 630 nanometer emission over Ahmedabad. And the estimated emission and the measured emission over Mount Abu, it shows quite good correlation for not only these nights, all other nights also. Now, apart from this monotonic decrement in emission, there are several occasions we have observed there is an enhancement in emission during the post-sunset time. Now here this red line, it shows the observed emission over Mount Abu. The black dashed line, it is the estimated emission over Ahmedabad. And this violet color, it shows the F-layer height variation, base F-layer height variation over Ahmedabad. Now, whenever the base F-layer height it comes down, we can see there is an enhancement in emission. Now here on this night, there is no enhancement, only monotonic decrement can be seen. So in the period of January, February, March in the year of 2013, 14 and 16, we have here overplotted those nights when we have observed the enhancement in emission during the post-sunset time. So this is all our geomagnetic quiet times, and this enhancement mostly observed during at the time of 21 local time. Now, what is the cause of this enhancement which observed during the post-sunset time? So the two factors can be mainly associated with this, the equatorial electrodynamics, the neutral wind. So coming first investigation of the equatorial electrodynamics, here we are showing the 4 nights. These 4 nights are in the same months and the same year. So it is expected that the background condition will not be changed too much. Now, out of these 4 nights, the first 3 nights, it shows the enhancement in emission. And this delta I, it shows the amount of enhancement which has been observed. Now, the 4th night, there is no enhancement, only decrement, monotonic decrement can be seen. In this row, the black line, it shows the base F-layer height variation over Trivandrum, which is an equatorial, deep equatorial location. Now, it is not also showing it do not show kind of contrasting behavior between these enhancement nights or non-enhancement nights. And this vertical orange color line, it shows the local sunset time. Then we move to the vertical drift during this evening time, sunset time. And DHDT has been calculated using the F-layer height variation over Trivandrum. So it shows this kind of vertical height variation. Now, in this night, the strength of the PRE is low compared to other 2 nights, but still there is an enhancement can be seen. Whereas the 4th night, the strength of the PRE is larger compared to other 3 nights. But if you look the observation of the 639 emission variation, there is no enhancement has been observed. Not only these 3-4 nights, all other nights during the period of January to March in the year 2014, here we are showing here. So on few nights are there is a strength of PRE is larger, but there is no enhancement has been observed. Here in this figure, the average drift during the period of PRE has been plotted here, and the y-axis it shows the delta I, the amount of enhancement. On several occasions, there is no enhancement has been observed, though there is a strong PRE was there present over the deep equator. So the equatorial electrodynamics was not able to answer for all the nights as a cause of this enhancement. Then I look the other factors, which is meridional wind. So as we know that the meridional wind, which can affect the plasma distribution over the off-equatorial region, the equatorward wind, it can move plasma vertically upward direction, whereas the poleward wind, it can brings down the plasma to the low altitude region. Now, during our observation period, there was no direct measurement of the meridional wind. Therefore, we use some earlier study when from Krishnamurthy et al., where they have estimated the meridional wind using the F-layer height variation between 2 stations, whereas one is equatorial station, another one is off equatorial station. Now the meridional wind over the equator, it do not show effect in the vertical movement. So with using this information, the meridional wind over off equatorial region has been estimated. Now in our case, we have used the equatorial station as a Trivandrum, and over Ahmedabad as an off equatorial station, we have estimated the meridional relative variation of the meridional wind over Ahmedabad, which is shown in this blue color line. And this red line, it shows the observed emission, which is observed over Mount Abu. Now, whenever there is an enhancement has been observed, in emission, there is a signature of the poleward wind has been observed. And the correlation coefficient between this measured emission and the meridional wind also shows quite well correlation. Now, in some earlier observation over the same location, Mount Abu, the meridional wind has been measured from Gurubaran and Sridharan, where they have measured the meridional wind, and it has been observed that during the sunset time, post-sunset time, around the time of 20 local time or so, there is a existence of the poleward wind. And whenever there is a poleward wind, you can see there is a base flare height that has been decreased, and it has been decreased to the altitude around 250 kilometer. So the base flare height, it is bringing down by the poleward meridional wind to the emission altitude of the oxygen 630 nanometer emission. So which causes this kind of emission enhancement. So as a conclusion, what you observe that the poleward wind or cessation of the equatorward wind, it seems to be responsible for this post-sunset emission enhancement in oxygen 630 nanometer emission over Mount Abu. Now, as I showed earlier, that during the period 2013 to 16, we have observed this kind of emission enhancement. And as the solar flux varies during this year, so we have plotted the delta I, that is the magnitude of emission enhancement with respect to solar flux. And it is expected that as the solar flux increases, the delta I value also increases. So as the solar flux increases, the ambient plasma also increases, so which reflects in the delta I value. Now here in this figure, we have plotted the delta I by I, the percentage enhancement of it, to remove the effect of solar flux. And this thing has been plotted with respect to day of year. So from January to March, the average trend, it shows that the delta I by I, it is decreasing. Whereas the PRE value, the P-reversal enhancement strength, it increases from January to March, from solstice time to equinox time. That is well known. Now these two are not correlated well. Whereas the climatological model HWM, it shows that the poleward wind that decreases from January to March, and which follows the similar pattern that we observed in the delta I by I. So it kinds of supports our earlier argument where we showed that the this poleward wind or the cessation of the equatorward wind is causing the enhancement in emission. So these results are published in Space Physics, so we can check it out. Now, as summary, here I discuss about the oxygen 630 nanometer nocturnal emission over Mount Abu. We have shown the post-sunset emission enhancement, which occurs mostly around 21 local time. So in this regard, the equatorial electrodynamics in the strength of PRE over Trivandrum has been investigated, and which is found to not to be responsible for this emission enhancement. Now then we investigated the poleward wind or cessation of the equatorward wind, which shows the better correlation with the post-sunset emission enhancement. And also the climatological wind model HWM14, which supported the seasonal variation of the emission enhancement, what we observed. So thank you for your kind attention. If you have any question, you can ask me now, or you can contact in my mail ID also. Thank you.
Thank you very much, Sovan. Very nice presentation. You have maintained time also. So we have time for some questions. I do not see any hand raised or anything in chat box. May I ask you, Sovan, one small query?
Yes, yes.
It's regarding like when poleward wind is there, then mostly the field, the geometric field lines, the force will be downward, downwelling will happen, isn't it?
Yes, yes.
So when we generally believe that our 630 nanometer airflow layer is maximizing around 220 kilometer and 250 kilometer, isn't it?
Yes, night time it is mostly basically around 250 kilometer.
250 kilometer. Okay, so when your basic ionization is coming down, then you have enhancement in the lower base of the effluent. That is what is the basic mechanism.
For here, it is what is happening. The flare height, it is coming down to the emission altitude of 250 kilometer. So
that's
it
what
is
I'm telling.
enhancing the electron density at that altitude. So it is
Correct.
causing.
So the poleward wind is known to bring down the layer, and then since your basic enhancement is peaking at 250, so you receive the enhancement at the air glow, and that you verified
Yes,
using
yes.
your anagram data, isn't it? Anagram data and this electrodynamics.
Yes,
also.
yes.
Okay.
Yes,
Fine.
yes, yes.
Thank you.
Yes, thank you.
Okay. Okay. Thank you for clarification. So then, thank you, Sohan. There are no more questions.
Okay, thank you.
We move to next presentation. Uh, next speaker is Sunil Kumar. Sunil Kumar, are you available?
Yes, sir.
Okay. So I invite you for a talk on 3D characterization of daytime gravity wave obtained using optical and radio measurements. Sunil Kumar is from Physical Research Laboratory of Ahmedabad. Please go ahead. Yeah, I can see your presentation.
Okay, sir. So good
Yeah, please.
afternoon, everyone. Myself, Sunil Kumar. I am a senior research fellow in Space and Atmospheric Science Division from Physical Research Laboratory, Ahmedabad. So in this talk, I will show the three-dimensional behavior of the gravity present in the daytime and as obtained by the using optical and radio measurements. And these will be the outline of my talk. So first of all, introduce about some basic and brief discussion about the optical and radio technique. So result and conclusion. So gravity waves are those waves where the force of gravity or buoyancy tries to restore the equilibrium. And so first of all, the dispersion relation of these waves given by the Heinz. So by using this dispersion relation, the vertical phase velocity and group velocity can be obtained, and these are looking like this. So from this we can say that the phase velocity and group velocity are oppositely directed, means when with time phase propagation is downward, then it indicating that a wave is moving upward. And these waves are generated in the lower atmosphere and propagate in the upward direction and deposit energy from one region to another region and play a significant role in the upper atmospheric dynamics and manifest the variation in the temperature, density, pressure, etc. So by taking the measurement of these parameters, we can study about the dynamics of the gravity wave. So in this work, I'm using Degelow emission. So Degelow emission can be used as a tracer to investigate the upper atmospheric dynamics. So Degelow are those emissions which are taking place in the upper atmosphere due to different photochemical reactions. In that time, to observe these Degelow emission is a very challenging task. So for that, I am using multi-wavelength imaging spectrograph, MICE. It is a high resolution imaging spectrograph and have resolution around 0.012 nanometer, and it has a large field of view around 140 degree and operate at 3 wavelengths simultaneously. And the output of this spectrograph is looking like this. So here x-axis pixel number representing the wavelength and y-axis pixel number representing the different spatial emission region from different view direction. So as you can see, there are three horizontal sections which are associated with three different emission lines: 630, 777, and 557. So by taking a horizontal component of this image, we just uh, match with the solar spectrum and subtract the solar spectrum, and by using the appropriate method as discussed in Palam Raju et al. 2013, obtain the Degelow emission as a function of time and spatial distance. So from this Degelow emission, we can infer the and we can investigate the gravity wave parameter in terms of in periodicity and as well as scale size. So let's see how we can calculate and derive these parameter of gravity waves. So here in this figure, for a given day, 5 February, the diurnal Degrolux emission is shown in the red color for 630 nanometer, and for a given time, the spatial Degrolux emission is looking like this. So by doing the spectral analysis of these variation, we obtain the variation which are present in the diurnal and spatial variation of the Degrolux emission, and these variation can be attributed to the periodicity and the scale size. And similarly, and another instrument is the digisonde. From that, actually digisonde provide the electron density profile. So by using electron density profile, we can estimate the vertical information of the gravity, and by using a method which is described in Mandal et al. 2019. So where what we do, we take the isoelectron density contour with time. So as you can see, there are some phase propagation in the downward direction. So to get a clear picture, what we do the periodogram analysis of all these isoelectron density contour, and as you can see that there is a common periodicity which is available in all these isoelectron density contour. So by doing the inverse Fourier transform of this particular periodicity, we obtain sinusoidal variation of isoelectron density contour. So as you can see, there is phase propagation in the downward direction, which is indicating a vertical propagation of the gravity wave, and from that we obtain the periodicity and vertical phase speed and vertical scale size. So for this particular study, what we do, generally the mice is oriented in only one direction, but for we want to obtain the spatial information in both direction, meridional and zonal. So for that, campaign mode observation has been carried out, where in the duration of 5 to 19 February, where the slit of the mice is oriented from meridional to zonal or vice versa is 30 minutes, and it is considered that in 30 minutes the behavior of the gravity wave does not change significantly. So in this fashion, we obtain the periodicity, meridional scale size and zonal scale size from the optical measurement. So by using lambda x, lambda y and tau periodicity, we can obtain the lambda is the horizontal scale size, which is can be calculated by k square equal to kx square plus ky square, and for a given day, let's say for 5 February, it is varying from 100 to 250 kilometer. So and the horizontal phase speed is also calculated, which is varying from 20 to 50 meter per second. On another day, the lambda s variation and ch horizontal phase speed variation are shown here, and the phase propagation angle can be obtained by using this formula tan inverse ky upon kx. But in this formula only give the angle with respect to the zonal direction, but to obtain the wave propagation direction, what we do the inverse Fourier transform of significant scale size with the time. So as you can see in meridional direction, the inverse Fourier transform has been carried out of a dominant scale size. So here, as you can see, for a given time, the trough and crest region are clearly seen. So if we trace a crest or trough region, then we can see in this plot that the crest or trough region are moving towards south direction, and in similar fashion it has been done for east west direction, and here it has been found that the wave are moving in the westward direction. So in this duration, all these days the gravity waves are moving in the southwest direction. So from optical measurement, we obtain the horizontal information of the gravity waves, and from the radio we measure the vertical information of gravity wave, let's say lambda z. So now we want to compare, and we want to estimate the lambda z using the information of lambda s. So go before there, I want to show the variation of the gravity activity with solar flux. So these plots are taken from the Mandal et al. 2020, where it has been shown that the number of gravity waves are increased as the solar flux is increasing, or it are shown in black line. So it is clearly showing showing a very good correlation between the solar flux with the solar flux, and in similarly the vertical phase speed are also shown with the solar flux, and it is also going with solar flux. So it is considered that the gravity wave activity and the vertical phase speed are increased as the solar flux increase, because at high solar flux time the dissipation force gets weaker, but at the low solar activity period these dissipation force play a very significant role, and in which molecular viscosity and thermal diffusivity play a main role. So in this background, as in the observation has been carried out in the 5 to 19 February 2021, where the solar flux values are almost around 7. So for that background, we are using a dispersion relation that include the dissipation force and is given by Vadas and Fritz. So where it is shown. So here omega is the intrinsic frequency, alpha is the function of wave number and scale height, and nu is the kinematic viscosity. So here we have the measurement from the optical data are omega I, kh, mighty instrument on onboard icon satellite, and other parameters are calculated by using model data. So using this dispersion relation, the lambda z has been estimated using the horizontal information of the gravity wave. So here the lambda h is shown in black color for 5 February, and horizontal wind variation in panel B of this figure are shown, which is obtained by icon satellite, and theta s is the phase propagation angle as discussed above, and theta u is the horizontal wind direction. So by using all these parameters, and the estimated lambda z are varying with time, and which is shown in black color line, and measured lambda z is shown in red color, which is obtained by the radio measurement. So as you can see on this day, it is showing a very good agreement with the measured value, and similarly for 7 February it is also showing a good agreement. So the conclusion of my talk that in the duration of 5 to 19 February, the horizontal phase speed, vertical phase speed, horizontal wavelength and vertical wavelength are varying like this, and in this duration the gravity waves are moving in the southwest direction, and the vertical scale size are estimated by using the measured horizontal information of gravity wave, and which are obtained by the optical measurement. And for a common periodicity which is available in the optical and radio measurement, for those gravity waves the estimated and measured vertical scale size are showing good agreement. Thank you.
Thank you very much, Sunil. Some results are very interesting actually. Before I comment, I would take some questions.
Yes.
I do not see any hand raising right now.
Okay.
Chat also, there are no questions. So if there are no questions from audience, then I found it interesting from 2 points of view, that when you do the radio measurement, we are doing the basic gravity wave parameterization using our like inosonde. If we are using, then we are using ionospheric parameter, isn't it? So the plasma
yes,
is the tracer, and when you do from optical, there also basically plasma is tracer, but the way the optical echoes are received, the optical signature, and the way the radio signatures are received are different. Like one is from reflection and another is from the line intensity. So
yes,
if they agree, means I mean, you can tell me now that assume that I have only the ionogram signatures. So shall I
Okay.
believe that more, or I still need to verify from optical signatures?
No, as we have shown that both are these showing good agreement, so you can believe. And from my senior also done a very nice work on the basis of this radio measurement, and he obtained the nice result where the total number of gravity waves show variation with solar flux and vertical phase speed. So yes, we can.
So and then there is a solar flux dependence of your basic gravity of parameterization also, like because of the viscosity and other thermospheric parameters will change. So you did for solar minimum, isn't it?
Yes, sir. The
So
observation period is.
what do you expect from your estimation for solar maximum?
Okay. Solar, if we use this dispersion relation, then it is better. But we also can use the dispersion relation where at the high solar flux time, when the dissipation forces are very less, as you can see here. Yes, where as you can see that this kinematic viscosity is inversely proportional to density. So at high solar activity period, the density is increased, so the molecular the viscosity is decreased. Yes.
So if viscosity is lesser, then how your basic estimation will change? Is there any effect of that on estimation?
Estimations, yes, definitely. If the let's say if there is no dissipation, as I can see in this result, as there is no dissipation, then the CH or lambda H can be increased.
Okay.
Okay, but so in let's say in high solar activity period, the lambda Z will be increased. Okay. You can say in that way.
Okay.
For the similar information of the horizontal.
Okay. Okay. Thank you very much, Sunil, for very interesting talk. Thank you.
Okay. Thank you, sir.
We move on to next talk in this session by Ravindra Pratap Singh, if he is available.
Nirvikar, he won't be able to make the presentation. That's what I understood. So I think we can move forward.
Sir. Okay, sir. Thank you for this information. Okay, so then we are taking the next presentation now. Varanasi Satya Shrikant from National Atmospheric Research Laboratory, Gadanki. Shrikant, are you available?
Yeah, I am available, sir.
Okay, yeah, so you are audible. Yeah.
Yeah, sir, are my slides are visible?
Yes, slide is visible. Yeah, now we are good to go. So the title of the talk is Discrimination of Doppler Shift in Atmospheric Gravity Wave Signature Due to Horizontal Background Wind Using Dictionary Learning Technique. Yeah, please go ahead.
Yeah. The present talk is on a machine learning algorithm for the discrimination of Doppler shift in gravity wave signatures due to horizontal background wind. Before analyzing for atmospheric gravity waves, it is essential to separate all the other sources due to winds, temperature, and planetary wave sources. So the most commonly used technique until now is the vertical filtering. But using vertical filtering, there is some loss of information. So to avoid that loss, we went through the machine learning dictionary learning approach. So the organization of the presentation is like, first we discuss on the parameters used for gravity wave signature analysis and multi-resolution analysis for decomposition of perturbation profiles. And we also give a brief introduction to background wind effects on atmospheric gravity waves. Later, I discuss about the methodology proposed using dictionary learning and the mathematical model formation and I also discuss like separation of this wind effects both in vertical wave number using space coding technique and in the frequency domain using Doppler correction using instantaneous frequency estimation. Later I discuss compare the retrieved Doppler profiles with radio sonde and meteor radar measurements, and we will finally discuss on seasonal variations. The most commonly used parameters for the gravity wave signature analysis are like temperature perturbations, velocity, and density perturbations. And we use the potential energy and Brunt-Weissler frequency for the analysis of the stabilities. Here, before analyzing each perturbation profile, we decompose each perturbation profile into different levels of decompositions with different resolutions using wavelets. Here we use the wavelet multi-resolution analysis technique in order to effectively calculate the background wind effect on signal decompositions. The effects of background wind on vertical wave number include like the background wind effect increase the vertical energy density at high frequencies, enhance the horizontal energy density at high frequencies, and transfer of vertical energy density to frequencies beyond the buoyancy frequency. And several models they don't consider the other effects of other wave phenomena. And one study reported by Ackerman reported that vertical wave number spectral densities will get attenuated. When the attenuated spectra will occur, there is a loss of information and they will push gravity waves towards the critical filtering. These variances and the vertical wave number trigger instabilities, and we cannot actually study the waves. And one study by Hayden et al. They reported the actual difference between the true measurements and the model measurement. They reported the difference of 15 meters per second and 10 meters per second in the mesosphere and the stratosphere for the zonal winds, and 10 meters per second and 5 meters per second for the meridional winds. Coming to methodology in this technique, first of all, we will train the dictionary using a good data of either temperature perturbations, density, or velocity perturbations, and we create one dictionary like called basis dictionary. Using for the test data, whatever we want to remove the background wind effect, we formulated it as a linear combination of these dictionaries. And once the dictionary is formed, we remove the Doppler shift effect using space representation in the vertical wave number domain, and later we use in continuation we use instantaneous frequency estimation technique to remove the Doppler shift effect in the frequency domain, and later we reconstruct all the individual decompositions into a single perturbation profile. In this technique, at each decomposition level, we learn all the individual dictionaries separately, and later we apply the instantaneous frequency estimation techniques. Here, equation 5 will represent the linear model combination, and the entire process mentioned in the block diagram here I have represented in the form of a mathematical expression as an optimization problem. So this optimization problem is solved using kernel singular value decompositions. In this, the component of background wind in the vertical wave number domain is removed through using sparsity. The effective metric for the representation of removing the background wind effect is the coefficient of sparsity, and it is the metric here we have to consider for the effectiveness of the algorithm. So after removing Doppler shift in the magnitude domain, we transform the we apply the same retrieved corrected profile to the instantaneous frequency estimation technique. Here in the instantaneous frequency estimation technique, what we do is we apply the short time Fourier transform and we calculate the instantaneous frequencies. From the instantaneous frequencies, we try to calculate the resampling factor through linear nonlinear curve fitting. So once we get the resampling factor, we are able to resample the original measured temporal resolution. So by resampling the temporal resolution, you can correct the effect of background wind in the frequency domain. So coming to the next question, how we will ensure that we have actually removed the background wind effects. So there are two metrics. One is the variance. The variance of temperature perturbation should be greater than 0, and the magnitude of perturbation should be less than the system uncertainty and the uncertainty introduced by the algorithm that is used for the temperature retrieval. If these two conditions are satisfied, then we can say there is no remnants of background remnants in the perturbation profile. After doing all this, we compared our methodology with using validated using ground-based measurements like GPS radio sonde and meteor radar. The methodology has a good correlation with good correlation at the lower heights between 24 to 32 kilometers with the GPS radio sonde, and at the meteor radar, the meteor radar heights between 70 to 80 kilometers. The difference is mostly due to the algorithm used for the temperature retrieval. So coming to conclusion, we applied this methodology for all the seasons in the year 2014. We observed that mostly this Doppler shift fluctuations are invariably varying in the summer season than compared to remaining other seasons, and they deviate more from Gaussian distribution function in the month of in the summer seasons. And the maximum Doppler shift value we can observe is 1.7 millihertz, and the minimum Doppler shift value observed is 0.32 millihertz. Yeah, thank you. Any questions are there? You can ask me, and or you can mail me also. Hello.
Yeah, thank you, Shrikant.
Yes.
Ramesh has put one question. K. Ramesh from SPL,
Okay.
I think.
Okay, sir.
Is asking that he is not sure why to remove the background winds, as the gravity wave intrinsic frequency is nothing but of Doppler shifted apparent frequency. What is its significance and may not mislead? So
No, sir. Because of presence of this background wind effect, actually we are treating instabilities also as a gravity waves. So in order to avoid that confusion, we are going for removal of this Doppler shift.
Okay. I do not see any questions. There is no hand raising. Yeah. So one reply has come. If we remove background winds, this may change the gravity wave properties.
No, sir. It won't change the gravity wave property, because the gravity wave frequency is in terms of hertz, and this is in terms of only in millihertz, sir. Means we cannot see much change in properties.
Okay, that depends actually. You may discuss it further. Maybe Ramesh can discuss with you in person and find the proper answer.
Okay, sir.
Yeah, he's also telling the same. He need to see this. Okay, so thank you, Shrikant.
I have one question, Shrikant.
Yeah, yes, sir.
Please. Yes, sir, please. Sir, question is not audible. Shrikant, can you listen anything?
No, sir.
Now it's okay, right?
Yeah,
yes,
okay.
sir.
The intrinsic frequency actually how you validate whatever you are got the Doppler shift, how you validate this one, because intrinsic frequency you will get when you subtract the this one phase speed of the wave and the wind in the direction of the wave propagation, then only you'll get the intrinsic frequency, right?
Yeah, yes, sir. What actually I will do is from the spectrum I will get the observed frequency, and through horizontal and meridional analysis I will calculate the Doppler shift using this radio sonde and meteor radar measurement, sir.
But
So
for
that
that one, you need a direction of propagation of the wave. That's what this U bar, what you are seeing, it is the wind in the direction of wave propagation. This is the crux of the problem, because we can get horizontal and horizontal winds, but we need a wind in the direction of wave propagation. Okay, just look at this one. Okay.
Okay, sir.
Yeah.
Yes, thank you, session chair Dr. Kishore, for expert comment. I think, yeah, thank you, Shrikant, and we'll move forward for next presentation.
Okay, thank you, sir.
Okay. Next presentation is by Somen Datta. Dr. Somen Datta from IIT Indore.
Yes, sir.
Somen sir, are you available?
Yes, sir.
Okay, so please load your presentation.
Okay.
The presentation is on detection of lightning-induced gravity wave from Navik signal and ground data.
Thank you, bro.
Is it visible, sir?
Yes, now, yeah, you please speak something so your audio can be verified.
Sir, is it visible?
Yeah. So yeah, now you're audible and your presentation is good to go. Please go ahead.
Okay, sir. Now I am going to present my research work, that is detection of lightning-induced gravity wave from Navik signal and the ground data. So to say something about this lightning-induced gravity wave, actually it generates from by the overshooting of this thunderstorm system, and it goes to this upwards and propagates by various atmospheric filtering processes such as wind flow and the chemical reaction and etc. The various models are there, so they propose that this propagation of this gravity wave mainly tuned by this by the geomagnetic field and the wind flow. So actually, so the main mechanism is that it actually generated and propagated to the upwards, and the thermospheric temperature gradient, which plays the key role on this filtering of this gravity wave. It actually persists under this under this thermosphere in a ducted mode, and and after that it leaked to the upwards and interacts to the ionosphere. So the main detection mechanism is the ionospheric ion density, total electron content density in a temporal manner. So if sorry. So to say, so the detection that is made, the if I say about the detection, so it first comes into our mind, that is the global navigation satellite system, because it actually operates in all weather conditions in a continuous way, and the basic equation that has been expressed by its observable, that is the pseudo range and this carrier pitch. The basic equation has been written. So there is not much to say that how to use this pseudo range and this carrier pitch observable for the estimation of this total electron content because it is well established. But this newly launched our Indian regional navigation system that is recently comes into this operation. So the TC estimation or total electron content estimation, these are not well known because firstly it is first and only it is using the S-band signal. So we have a this NAVIC receiver that is the that was installed in the rooftop of the Indian Statistical Institute, Kolkata. The latitude and which is a dual frequency receiver which logs actually the dual frequency IRS signal L5 and the S1 and the single frequency GPS signal. So the location of this receiver has been given, that is the latitude is the 22.6488 north and the longitude is the 88.3767 east. So before this estimation or this main equation that is written here, that is using the differential code and or the differential phase, we need to correct in some way. Some of this correction is very much required for this accurate estimation of this TEC. So first is the cycle slip detection, which is actually presents in this carrier phase delay, and it has been corrected by us by this Melbourne-Urbana combination, well-known Melbourne-Urbana combination, and after that, which is a narrow lane board and the wide lane carrier phase combination, and after that we do the time series of that Melbourne-Urbana combination to the singular value decomposition, and we find the cycle slip detection, and it has been detected very well. Then the phase window correction. Phase window correction is a very minimal correction, but for the accurate estimation, it is very much required because sometimes due to this, actually this the location, the position of this antenna of the satellite, it actually fixed to the coming of the sunlight. So there is a movement with respect to the receiver of this satellite antenna. So sometimes, so in a temporal manner, it actually some additional phase is changing in due to this movement of this satellite antenna. So this phase window correction is also required. So it has been corrected based on this position of the sun and the local coordinate system of this local body coordinate system of the satellite, and as well as the ECF coordinate system of this receiver. Then the satellite antenna phase center correction, actually from this 2015, the IGS, the International GNSS Service, they provides the phase center of this, they includes the phase center of the INSS satellites also. So this phase center, yeah, actually we have taken the broadcast of this satellite orbit information, that is the broadcast orbit, not the SP3, because it is not available. So for this from this broadcast orbit, actually the location of this satellite is given, what is estimated, that is the actually the antenna position. But the differential phase, which is very much required for this ionospheric correction, so the satellite antenna phase center correction is also included. And another is the carrier phase based code smoothing. We calculated in this total electron content or the INO delay, both on this carrier phase measurement and as well as the pseudo range measurement. So we use a H filter algorithm. It is a very well-known algorithm. This based on this change of this carrier phase, we smoothed the pseudo range measurement because the pseudo range is a very noisy measurement compared to this carrier phase. So that's why it has been included. So after that, that is which is required. That is the biasing factors for this. The biasing factor is mainly very much dear, and we couldn't remove this biasing. one is the carrier phase ambiguity, another is the differential biases. These are so the differential biases has a very much low frequency of this changing. So that's why we considered that whatever is the biasing, that is the carrier ambiguity or the differential code bias, or are included in a same biasing manner. So that's why we here applied the adaptive Kalman filter for the very accurate estimation of this differential phase bias or the ionophile ambiguity bias. And by doing the all needed correction, such as the tropospheric correction and even if tidal correction and all this least possible correction that has been done here, and then applied that thing, this V rho IF and V phi IF. This is the ionophile combination of this carrier phase and this pseudo range, and these are the very after incorporating all this correction, these are the measurement, and we have estimated this ionophile combination of this ionophile ambiguity factor, that is the NIF. And we also measured the ambiguity factor from a single frequency measurement of this carrier phase, and we estimated that what is the amount of carrier phase bias is there, this what amount of ambiguity is there, and this ambiguity factor, it is which includes the ambiguity as well as the various biasing terms also. So actually, it is the best way to for the application of this least square algorithm by a dense network. But we have a single receiver, so dense network by this IRNSS constellation is not possible. So that's why it cannot be possible. So by this single measurement, I have done this thing. And after the application of this iono delay measurement, we have done this receiver bias correction that has been described very well by Ma et al. 2013, and the satellite frequency biases that has been corrected by the timing group delay measurement. So these are all correction. So let's come to this. What is the lighting? That is April 1, 2018. I have taken the lighting information has been taken from this WWLLN Worldwide Lighting Location Network, which gives the information that what is the intensity of this lightning and what is the position of this latitude, longitude of this lightning. So here it is showing that lightning location, that it is showing in a very small zone. There is a very severe lightning event occurred towards the eastern part of this or the coastline of this Bay of Bengal, and very almost 20,000 lightning strikes occurred in this region on that day. So lightning statistics has been made based on this lightning strikes. That is we have calculated the every 2 degree cross 2 degree this grid of this latitude longitude, and find the average the number of lightning strikes for each hour. So the lower two histogram diagrams. The first histogram diagram that gives what is the at which time this lightning strikes occurred, and it has been assumed that that this figure indicates that it started from the 10 UTC 10 AM, and it reaches its peaks towards at this before 15 PM, and gradually it decreases. So based on this position of the lightning strikes, that we want to know that what is the possible location of the source of this gravity wave. So we assume that what is the most dense region, most dense grids with respect to this lightning strikes, that is the possible reason of this generation of this gravity wave. So that's why
I think you have already consumed 12 minutes. Please come to the results.
Okay. So these are the lightning zone that has been included. So we have So we have taken the this from this UNAPCO network, from this Bangladesh GNSS network, and from this INSS receiver. So first we observe that what is the absolute total electron content, both from this INSS measurement and as well as the GPS measurement. And we found from the GPS measurement we found that there is a very good perturbation in this total electron content measurement, which has been also showing in this INSS measurement also. The gravity wave measurement has been gone through this way, that is Ting et al. It is a that is after this sampling this sampling difference of this total electron content measurement. So it is the gravity wave signature. So signature both from measurement from this GPS signal and as well as this INSS signal. So it has been from this we have taken this from these two from the two GPS GPS satellites from this all four UNAPCO GNSS receiver and as well as the GNSS this INSS signal, and it shows that a perturbation of 0.6 TSU is observed from this measurement. And another interesting thing that is that this perturbation has a very good based on this location, that there is on a very far location from this lighting zone, there is a good perturbation has been observed. So the time frequency plot which has been time frequency plot is showing that there is from the from this fourth station, that is there is a two dominant frequency mode. One is almost near to 5 millihertz, and another is almost 1.7 millihertz is observed. So in the near station, that is 5 millihertz is very dominant. That is the INSS measurement, and next are the GNSS measurement. But gradually this 5 millihertz dominant mode it decreases and attenuated, and 1.7 millihertz very is very prominent for this all these measurements. So thank you.
Thank you, Suman, for good talk. I will take maybe a quick question if somebody is raising the hand. I do not see anything here in chat box also. Says almost nothing is there. Just one quick reply you make.
Yes.
For estimation of TC,
Yes, sir.
Generally we take the dual frequency difference.
Yes, sir.
You have done some corrections on the carrier phase and all.
Yes, sir. Yes, sir.
That is for GPS data or for IRNSS data?
For IRNSS data, I took it.
For IRNSS.
And as well as for the GPS data, but the results it is showing that is not the GPS data. I have not corrected that thing. The validation of my correction based on this GPS and the IRNSS is not here, but that is the well-known software I have used for this GPS measurement, and validated this time frequency measurement with the IRNSS signal.
No. When we talk about differential measurement, which is like difference on one frequency delay on another frequency.
Yes, yes.
And then phase wind up is something you told something about phase wind up. What is that?
Yeah. Phase wind up is very much required.
Why it happens?
Because the satellite position, location, the satellite antenna actually it antenna location is changing, because the satellite orientation is very much dependent on the sunlight coming up.
Why sunlight is coming in?
Because it is fixed in this way that the solar panel is directly perpendicular to the sunlight.
So I got your point, because the panels will be arranged for the purpose of maximum energy for satellite, so they have to rotate the satellite orientation. Okay, actually you should relate directly. Tell it that because we use GPS signal as RSCP, right-handed circularly polarized. So that correction comes because the satellite is moved and which is not expected on the carrier phase. Anyway, okay, so these are two clarification. I think if there's nothing else, then we'll move for the next talk.
Okay, sir.
I do not see any
Thank you.
questions. Thank you, Suman.
Yes, sir. Yes.
Thank you. Yeah. So now we are 4 minutes late. Thanks to one presenter who is not available. We are still on time. Next presenter is Gaurav Mitra.
Yes, sir. Am I audible?
Yes, Gaurav.
Is my screen visible?
Yeah, it is not on full screen mode. Please.
Yeah, I'm doing that.
So Gaurav will
Now,
talk about planetary wave dynamical variability at low latitude middle atmosphere during September 2019 SSW. Yeah, this is the title.
Yeah, I guess it's in full screen mode.
IIT Gandhinagar. Yeah, everything is good. Please go ahead. He's from
Okay,
IIT
fine,
Gandhinagar.
perfect. Thank you.
Yeah. Oh, he's from PRL, Physical Research Laboratory.
Yeah, I'm from physical. So, good evening, everyone. I'm Gaurav Mitra, Senior Research Fellow in the Space and Atmospheric Sciences Division, Physical Research Laboratory, Ahmedabad. Today, I'm going to talk about planetary wave dynamical variability at low latitude middle atmosphere during September 2019 sudden stratospheric warming. Occasionally during winter, the meridional circulation gets highly disturbed, accompanied by marked amplification in planetary waves. This event is also characterized by considerable deceleration of the zonal mean westerly winds and sometimes reversal into easterly wind as well. Simultaneously, the polar stratospheric temperature increases considerably by few tens of kelvins within a few days. This particular dramatic warming event is known as sudden stratospheric warming. The sudden stratospheric warming event is initiated by enhanced planetary wave activity, which decelerates or weakens the eastward flowing jet stream by inducing their westward momentum, and as a result, the jet stream starts meandering along the latitude. As a result of this weakening, the polar vortex also becomes unstable and it may either get split or displaced from its position. And this results in adiabatic heating as the air in the vortex gets compressed. Moreover, it also results in the movement of cold air from high latitude to low latitude and also movement of warm air in the polar direction. Major and minor warmings are two main categories of the SSW event. Reversal of zonal mean temperature pole out of 60 degrees is the signature of both major and minor event, but the reversal of zonal mean zonal wind at 60 degree latitude and 10 HP pressure level is the characteristics of a major warming as per the definition given by Lewis Kenozotor. Another important point to keep in mind is the occurrence of SSW is more frequent in the northern hemisphere than in the southern hemisphere. This is primarily due to two reasons. Firstly, there are higher planetary wave activity in the northern hemisphere than in the southern hemisphere because of higher orographic difference and land sea contrast. And secondly, the cumulative wave flux requirement to cause SSW in the southern hemisphere is more because of stronger polar jet. Few notable studies on the impact of 2019 southern hemisphere SSW event affecting the global atmospheric system are as follow. Such as Noguchi et al., who reported enhancement of convective activity in the tropics of the southern hemisphere, and Musin Yamazaki observed 6-day oscillation in the ionosphere pertaining to this warming event. Another important information is that in the southern hemisphere, as I've already mentioned, SSW event is a rare event in the southern hemisphere. Until now, major SSW event occurred way back in 2002. Recently, a minor but impactful SSW event occurred in September 2019. Although SSW event is a polar stratospheric phenomena, it has potential to impact the global atmospheric system from the troposphere to the thermosphere and also across both hemispheres. Although there has been studies on ionospheric variabilities and convective variability during this dynamic event, there is hardly any literature on the middle atmospheric dynamical variability during this dramatic warming event. Henceforth, I'll be discussing few results on the same event. This following figure shows the background dynamical condition during the September 2019 Southern Hemisphere minor SSW event. For the present work, we have used the following observational parameters such as the horizontal winds, where U denotes zonal wind and V denotes meridional winds from meteor which provides data in the vertical coverage 80 to 100 km, and ECMW data, which provides model level data in the vertical coverage 0 to 80 km. Additionally, we have also utilized temperature data from ECMW free analysis dataset. The first figure shows the latitudinal profile. The left column shows the difference between the zonal mean temperature and the temporal mean of zonal mean temperature, and the right column shows the zonal mean zonal wind. The first figure shows the latitudinal profile at 10 HP pressure level. And the remaining figure shows the altitudinal profile at 60 degrees south, 22.7 degrees south, and 7.4 degrees south, respectively. Why 22.7 degrees south and 7.4 degrees south are chosen because these are the latitude of our meteorite observational location. And we observed noticeable warming, and we have chosen observational days from 1 August to 31st October, which is centered around the warming event. We have observed noticeable warming greater than 25 Kelvin in the high latitude between day number 253 and 263, which is considered as the warming period in our current study. We have also observed considerable deceleration of the zonal mean westerly winds at the onset of the warming event. However, there is no reversal at 6 degrees south and 10 HP altitude. But we observed this reversal of in zonal mean zonal wind in the upper stratosphere. So this particular warming event can also be termed as high stratospheric warming, according to Sevenkova. Moreover, we have observed stratospheric warming at middle latitude and mesospheric cooling during the warming days. However, in low latitudes such as 22.7 and 7.4 degrees south, we observed stratospheric cooling and mesospheric warming during the warming days. So, to sum up, we can say that the low latitude middle atmosphere shows contrasting behavior with respect to middle latitude middle atmosphere. Moving on to determine the involvement of traveling planetary waves during the warming event, we have used the wavelet analysis using Mollet as a mother wavelet. And the first column shows the zonal wind wavelet spectra at Cacho de Palusta, which is our extratropical meteorite observation location. And the right column represents the same for Caridi, which is our equatorial meteorite observation location. For the 90 kilometer, we have utilized the meteorite data, and for subsequent to altitude, we have utilized ECMWF data. The y-axis represents the time period, and the x-axis represents the observational days. We have identified few major traveling planetary waves, such as quasi 16-day waves, or period 14 to 20 days, primarily in the stratospheric altitudes during the pre-warming days. And we have also identified a quasi 60 waves, primarily in the upper mesosphere MLT region, which exists during the initial days of post-warming phase. And we have also identified quasi 10-day waves of 9 to 12 days, which exist in the pre-warming days. Next, to determine the direction of propagation of the major traveling planetary waves, we have done wave number period vector utilizing horizontal wind data and feed those horizontal winds data with the given equation, where capital A is the amplitude of the wave, capital T is the time period, S is the wave number, lambda is the longitude, and phi is the phase. The positive phase value implies westward propagation, and the negative phase value indicates eastward propagation. The left column shows the zonal wind wave number Fourier spectra at CP latitude, and the right column shows the same for CL latitude. The y-axis represents the time period, which is the periodicity in temporal domain, and the x-axis represents the periodicity in spatial domain, that is wave number. So the already identified waves, previously identified waves, such as the quasi 6-day waves, quasi 16-day waves, and quasi 10-day waves, are also found in this wave number Fourier spectra, and they are all found to be traveling westward, predominantly corresponding to zonal wave number 1 and 2. We looked into the activity of stationary planetary wave dynamics. We observed significant dominant activity of stationary planetary wave number 1 and stationary planetary wave number 2, which are particularly active in pre-warming condition, particularly at 1 HPA pressure level, that is at upper stratospheric level, and they are found to diminish at the onset of the warming days. Moreover, we find that the amplitude of stationary planetary wave number 1 is greater than the amplitude of stationary planetary wave number 2, which indicates the salient role of stationary planetary wave number 1 in preconditioning the warming event. Further insight into the meridional air mass mixing and instability is provided by the potential vorticity map. We know that the breaking of planetary waves causes mixing of air mass between the low and high latitudes. We observe noticeable intuition of low absolute potential vorticity value from low latitude to high latitude during the warming days, as observed in this figure. According to Charniston-Pedlowski criteria, a reversal in the sign of the meridional gradient of the background flow is a necessary condition for the growth of waves. We have identified a dense patch of negative meridional PV gradient in the latitude range 20 to 40 degrees south between DA number 230 and 263, which indicates significant instability and probably and may be responsible for exciting the quasi 6-day waves, which are found to be present during the initial days of post-warming phase, which is in accordance with past studies. Further diagnosis of the wave energy propagation and its forcing on the main flow is provided by the Ellison Plum flux. F, where F points in the direction of the planetary wave propagation. The F is represented by these proxy vectors in this figure, where the first component of F represents the meridional flux of zonal momentum, and the next component shows the meridional heat flux. Where rho naught is the density, is the Earth radii, phi is the latitude, phi is the meridional wind, and u is the zonal wind, F is the Coriolis parameter, and theta is the potential temperature. Here the prime value indicates deviation from the zonal mean, and the overbar indicates zonal mean value. We have also computed the divergence of F, where wave driving D is proportional to divergence F. Now let's understand the physical significance of this wave driving D. When wave driving D is greater than 0, it indicates divergence, which indicates possible source region of planetary waves. And when this wave driving D is less than 0, it indicates convergence of planetary waves, possibility of planetary wave breaking, and this decimation of mean energy to the mean flow. For the present study, we have chosen individual days such as 10 September, which is a pre-warming day, 14, 18, and 21 September, which are warming days, and 24 and 27 September, which are post-warming days. The efflux diagnosis shows the propagation of planetary waves from high and mid to low latitudes during the warming, as illustrated in this latitude height cross section of the efflux and this divergence. And we find that this wave flux intensifies during the warming days, with maximum wave flux on the peak warming day, that is 18 September, and henceforth the wave flux diminishes considerably after the warming days. The present work portrays the planetary wave dynamics in the middle atmosphere during a minor but impactful SSW event in the September 2019. Based on the observed feature, we can say that the present warming can be categorized as high stratospheric warming. We have also observed contrasting behavior in the low latitude middle atmosphere with respect to high latitude. Moreover, we have observed, identified a strong cos 16-day wave, which are primarily found to be present within the warming interval in the stratospheric altitude, followed by the occurrence or outburst of cos 6-day waves, which are found in the mesosphere and MLT during the initial days of post-warming days. And we have also identified the few traveling planetary wave components such as cos 16-day waves, cos 10-day waves, cos 6-day waves, and cos 3-day waves, and all these are found to traveling westward, primarily corresponding to zonal wave number 1. Further, the current study points out the dominant role of stationary planetary waves with zonal wave number 1 in preconditioning the event. We have also seen significant latitudinal mixing of air masses as evident in the potential vorticity map. Further, the growth of cos 16-day wave is probably associated with the instability as revealed from the negative meridional gradient computation. And we have the efflux further reveals that reveals propagation of planetary waves from high and mid to low latitudes during the SSW event, which maximizes on the pre-warming day, that is 18 September. Thank you. If there is any question, please ask.
Yeah, thank you, Gaurav. Any questions from participants, attendees? I do not see any. Yeah. Question from K. Ramesh of SPL is telling that the talk is interesting. I wish to know that what is the mechanism for mesospheric cooling during SSW event?
Yeah. So what happens actually it's an interplay, like the temperature gradient kind of reverses during the SSW event. The polar stratosphere it's comparatively warmer compared to the low latitude. So there is a change in the temperature gradient. As a result, there is a change in meridional circulation. So as a result, there is upwelling of air, which results in adiabatic cooling in the mesosphere. This is one reason. Another reason, possible reason, can be that there is significant wave dissipation in the stratosphere. And we know that mesosphere temperature is mostly controlled by waves. So if there is wave dissipation in the stratosphere, there is less chances of dissipation in the mesosphere. So that may also result in mesospheric cooling. I hope I answered.
Yeah, can you give like this mechanism what you are telling is referred in any previous study or in your paper?
Yeah. This has been referred. I can't recall the name of that paper.
Okay,
but
fine. Yeah. It is available. Okay.
Yeah, it's available. It's okay. This work is published in JGR Atmosphere.
Okay. Okay,
find
so
the
people
people.
can follow it. Okay. Another question by Akash Kumar. He
Yeah.
says that is a nice talk and he's asking how QBO affect the SSW occurrence in SH. SH, I believe, southern hemisphere.
Yeah, southern hemisphere. Yeah.
Okay, so please answer how QBO affect the SSW occurrence in SH.
That I haven't looked so far. So yeah, there has been studies which has shown that QBO has effect, but I need to study to give a proper explanation. So at this moment, I can't give a proper reply. I'm sorry,
Okay.
extremely sorry.
Okay. Okay, I have one quick query that you have done from Brazilian sector, na? These observations are all
Yes,
from Brazil.
yeah. From Brazilian equatorial and extratropical location.
Is there any study on this event from Indian or similar study from our sector?
Yeah, I've seen one paper. They have shown they have taken some observation from Tirupati and they have shown some planetary wave dynamical variability. Apart
Okay.
from that, Noguchi has shown that has shown convective variability. Interestingly, shown that the convective activity increases in the Indian region due to this.
So I want your comment on the longitudinal differences because this event is reported from different longitudes.
Yes.
Because you are talking about the traveling quasi waves and even stationary and also the comparison. So how does it affect your 2 or 3 longitude separation when we are making? Please comment on that.
Yeah, that can you repeat your question because I want to properly understand your question.
Yeah, question is that since the event is global,
yes,
and you have observed the quasi 16, 6 and 10 day propagating waves, westward propagating waves. So how does different longitudes will react? Do you see the similar signature on similar day numbers from the event, from the day of the event, or there is a delay or like that kind of?
Yeah, that will be an interesting task that we haven't still carried on. But yeah, there may be some interesting features that we may look. But while calculating this wave number pair spectra, we have taken into consideration all the longitude, which is available from ERA 5 data because it's longitudinally contemporaneous. It provides longitudinally spaced contemporaneous data. So we have seen similar signature throughout the globe. These are all global waves. Probably there may be some phase difference. Yeah, that we may look into longitudinal differences as well. So yeah, that's an interesting task.
Okay, then thank you, Gaurav, for very.
Yeah, we will. Thank you.
Hello, anybody is there? Okay, thank you, Gaurav. Then, so now we move on to the last presentation of this particular session in PS2 for today. This is Venus Venugopal, Dr. Venus Venugopal from Space Physics Laboratory, ISRO, and he would talk on response of Brewer-Dobson circulation to SSWs over the northern and southern hemisphere. Dr. Venus, are you available online?
Yes, sir.
Okay.
Is it visible, sir?
Yeah, now it is full screen visible and you are good to go. Please go ahead.
Thank you, sir. Good evening, all. I'm Venus Venugopal from Space Physics Laboratory, VSSC. I'll be presenting today the response of Brewer-Dobson circulation to sudden stratospheric warmings over the northern and southern hemisphere. I'll be using observations as well as modeling for the analysis. The Brewer-Dobson circulation was first proposed by Gordon Dobson and Alan Brewer. Dobson observed the ozone distribution of the stratosphere, and Brewer, from water vapor measurements, proposed that there should be a circulation which has upward motion in the tropical region, meridional motion in the stratosphere, and downwelling motion over the high latitudinal region. So the circulation, essentially called Brewer-Dobson circulation, BDC, is driven by the wave breaking and the westward force imparted to the mean flow by the breaking of waves. So this is a sense of the circulation plotted from ozone number density from Aura MLS measurements. So you can see, if you concentrate on the northern hemisphere, it has got seasonal differences and also in the hemispheric differences. So the circulation is more intense in the winter season over the northern hemisphere during January, February, December, January, February. And you can see more ozone concentration over the polar region during that time. And also when the southern hemispheric winter, the ozone concentration is high over the southern hemisphere. And also the very low concentration over the southern hemisphere, which is not observed over the northern hemisphere due to the intensity change in the circulation. The circulation is more intense in the northern hemisphere because the wave activity over northern hemisphere is much higher than the southern hemisphere part. Also, you can see from the tropical region where the source production region of ozone, the ozone is transported by the circulation to high latitude regions. So sudden stratospheric warming was explained by the previous speaker. So these are characterized by sudden increase of temperature over the polar cap. And if it is accompanied by a reversal in the climatological wind direction, then it is called a major warming. If not, then it is called a minor warming. So the present study will be considering the variation in intensity of BDC, blue adoption circulation, in response to SSWs, and specifically how it responds differently to northern and southern hemispheres. These are the database that we'll be using: ORA-MLS, ozone sonde measurements, URA5 and GeoSCAPE model output only. So the northern hemisphere, this is for 2005, which was a non-SSW period from January to February. And this is 2006, which observed a major SSW. So you can see from here that the blue color line, which shows the zonal wind, throughout this period, the wind is always in the eastward direction. But for the SSW year, the wind reverses from the eastward direction, the climatological eastward winter time direction, to westward direction. And it also retains its eastward direction after a period of time. Also, it shows an increase of temperature along that period. So this shows a major SSW. And similarly for southern hemisphere also, you can see the blue line, the zonal wind is always in the eastward direction, whereas for 2002, which observed a major SSW, you can see from the eastward direction, it is changing to westward direction. And after some time, it reclaims its climatological eastward direction. So as previously said, there was SSWs are rare in the southern hemisphere. For this analysis, we have taken the 2002 and 2019, which was not a major SSW. Wind reversal was not there, but we have taken these two for the analysis. So to analyze the blue adoption circulation's intensity, we have taken the diabatic heating rate. So the tropical upwelling would, in the tropical upwelling part of the circulation, would cause the air parcels to adiabatically cool. And then when the parcels found themselves cooler than the surroundings, they will diabatically heated up. So this diabatic heating rate can be used as a proxy of the intensity of blue adoption circulation. So we have plotted blue adoption diabatic heating rate for SSW period, which is shown in red, and non-SSW period, which is shown in the gray color. This is for southern hemisphere and this is for the northern hemisphere. For the SSW period, this diabatic heating rate is much more than the non-SSW period. And similarly for northern hemisphere also, you can see an enhancement of diabatic heating rate compared to non-SSW period. So to analyze the wave activity during this period, this is for southern hemisphere and this is for northern hemisphere. And this is before the SSW peak periods, and this is during SSW peak period, and this is after the SSW. So you can see the epiflex divergence that is plotted. The blue color or the negative values shows divergence and breaking of planetary waves, and westward force imparting to the mean flow. So before and during the SSW period, you can see high amount of wave breaking, which would drive the circulation. And just after the SSW period, you can see very less blue patches. That is very less convergence of wave in the southern hemisphere. Similarly, for northern SSW period, you can see much more high wave convergence. And after the SSW, it is reduced to the wave activity is much reduced, but it is not as drastically reduced as for southern hemisphere SSW. So to analyze the mean advective trace transport, we have plotted the residual mean meridional stream function RMMSF, and for this positive RMMSF denote clockwise transport, which is shown in red color, and negative values denote anti-clockwise transport, which is shown in blue color. For the southern hemisphere SSW period, as per the previous plot, this is before SSW period, this is during, and this is after SSW period. So before the SSW period, you can see the enhanced wave activity drives the circulation, and more trace transport is observed, and which diminishes drastically as SSW after SSW. And also for northern hemisphere, the more transport is observed over this region, this period, but it is not as drastically reducing as the southern hemisphere counterpart. So the variation in Brodopsin circulation would result in changes in stratospheric distribution of ozone and water vapor. So this is from India Meteorological Department, Thiruvananthapuram data, ozone sonde measurements. You can see before the SSW dates, 18 and 15, around the 18 and 25 January 2006, you can see a decrease in ozone sonde measurements. This could be a localized phenomenon, so we have plotted from ORI-MLS measurements. This is for tropical region, and the bottom panel is for polar region. And this left panel shows southern hemispheric SSW, and right panel shows northern hemispheric SSW. And you can see a decrease in ozone measurement over the tropical region for the southern hemispheric SSW for 2019. And also correspondingly, you can see an enhancement in ozone measurements over the polar region. Similarly, for northern hemisphere, a decrease over tropical region and increase over polar region is observed. So this has been confirmed with model outputs. You can see model reproduces the pattern observed from ORI-MLS measurements. This is for the non-SSW period for 2005, and this is for 2006 SSW period. You can see that the pattern is reproduced by the model, geoscale model, in the ozone measurements. So this is from tape recorder effect. For the SSW period, you can estimate the Brodopsin circulation speed approximately to be 3 into 10 raised to minus 4 meter per second. And for non-SSW period, it is found to be 2 into 10 raised to minus 4 meter per second. Also, the much more dry air is transported to the stratosphere from the tropospheric region during SSW period, which can be seen in this part. So to summarize, the wave driving after SSW in southern hemisphere is drastically reduced after the event compared to northern hemisphere, and which is also reflected in residual mean meridional stream function, which also has a significant reduction after SSW compared to northern hemisphere. And also this transport more ozone from tropical region to polar region, and the intrusion of dry tropospheric air into the stratosphere during SSW period is also observed. Thank you.
Thank you, Venus, for a good presentation. You have maintained time also.
Thank you.
There's a question coming, hand raised by Shashi Singh. Yeah, please go ahead. Shashi Singh. Yeah, please. We are not listening anything from Shashi Singh. They are raising hand but not speaking.
Can he type his question in the chat box if there is a problem in the audio?
There are other questions
In the
coming.
meantime, we can take other questions.
Yeah. So, one Akash Kumar is wanting to know what is the information or formation mechanism physics of BD circulation in southern hemisphere. Did you listen the question, Venus? Hello.
Hello, am I audible?
Yeah. Yeah, now you are audible. So you please listen the question. What is the formation mechanism physics of Brewer-Dobson circulation in southern hemisphere?
Yeah,
That is
thank
the
you for the
question.
question. So the circulation is essentially driven by breaking waves. The planetary Rossby waves, when they break in the atmosphere, when they meet a critical layer, they impart a westward force to the mean flow, which on the action of Coriolis force, it is advected to the polar region. So also the mass continuity drives in the tropical region. The air is driven to the stratosphere, and this is the mechanism by which, or both regions, it is driven. But in the southern hemisphere, due to in the northern hemisphere, there is a land sea temperature contrast. So the Rossby wave is much more frequent and intense. Also the orography of northern hemisphere. So it is much more intense over the northern hemisphere than southern hemisphere.
Okay, I hope you might have received the clarity on this. Okay, we'll go for next question. Dr. Ramesh is asking, is there any reason or mechanism for larger EP flux in northern hemisphere than in southern hemisphere?
Yes, as the same answer. The wave activity is much higher over the northern hemisphere. That is the reason, and also the southern hemisphere does not see that much wave activity, which is the reason for the lesser EP flux.
Okay. Okay, then I do not see any other questions for your presentation. So then thank you, Venus. And
thank you, sir.
I thank you all the presenters of this session and all the attendees, all the participants of this session. I also especially thank Ramesh. Okay, there is a question coming. Venus, are you online?
Yes, sir. Yes, sir.
Akash Kumar is again, but the direction is opposite in both the hemispheres for the Brewer-Dobson circulation. So he may be asking why the direction is opposite if the same mechanism is there.
The direction changes would be when the wind is flowing from when we are considering the thermal wind direction, it would be from in the both hemisphere. It will be from when it is flowing from equator to northern hemisphere, it will be deflected towards right by the Coriolis force. So the thermal wind effect would result in a rightward direction. So yeah, that is.
Okay, I think that is textbook information. Okay, so yeah, thank you, Venus, and I thank all these presenters. Special thanks to Ramesh for keeping the chat box busy. Maybe he can come for the audio questions also. It will be interesting to have a interactive question answer with the speakers. With the chat box, we can throw a question, but answer comes whether we are also not sure whether the answer is able to satisfy the query. Anyway, query for this question, people asking questions. Okay, so I hand over with this the session proceedings to Dr. Tarun Kumar and the session chairs at SPL. Tarun sir.
Yeah, thank you, Nirvikar. It was a nice session. As you know, as you said, if more people could participate in the discussion, it would be very nice. But unfortunately, a little bit of time constraint, I think that kept us from having more discussions.
Yes, sir.
But if I think if we request all the presenters, maybe the coming sessions, if they can restrict it to their presentations to maybe 10 to 12 minutes, then there will be enough time for discussions.
Yes, sir.
So I completely agree with you. The more participation, more discussion would make it more lively.
Yes.
So thank you. So on behalf of Nirvikar and me and Kishore and Subramaniam here, we thank all the presenters for today's sessions, PS2. So thank you very much. And over to LOC.
Thank you. We thank all the moderators of this session, Dr. Kishore Kumar K, Dr. Tarun Pant, Dr. B. Bala Subramaniam, and Dr. Nirvikar Dashura for moderating the second day of plenary session 2, Middle Atmospheric Coupling, Dynamics and Climate Change. We thank all the presenters for their wonderful presentations and for this engaging session. We will meet again tomorrow for the third day.